Hello and welcome to our program Physics of Music. Well, science is an integral part of everybody's life. Whatever we might do, there is science behind it, and music is no exception. Why is music different from other sounds? What makes music pleasant to the ears? We'll find out the answers to all these questions and much more with a renowned expert. We have with us Dr. Partha Ghosh, a renowned physicist of the country. Dr. Ghosh, a warm welcome to the program.
Thank you.
And before we move on to talk about the details of physics and music and science, for the benefit of our viewers who are non-science students, tell us how exactly is sound produced?
Well, it depends on what is producing the sound. I can drop something and that will produce a sound. Or I can play a musical instrument that will produce a sound. I can strike something with a hammer that will also produce a sound. So what basically happens in all these is that whatever is struck is set into vibrations.
Okay.
And these vibrations are transmitted to the air around it. So the air starts vibrating in the sense that there are compressions and rarefactions of the density of air, and that travels with a certain velocity, which we call the velocity of sound.
True.
And when that goes and impinges on a human ear or anybody's ear, it goes and excites certain vibrations inside the ear, and those vibrations are converted into neurosignals, electrical signals, which then go to the brain, and the brain interprets those vibrations as sound.
That's true.
That's what basically happens.
Yeah. But what makes music so different from other sounds? And we are, even lay people who don't have much of a knowledge about music, they are able to distinguish that this is a musical kind of a sound.
Yes. This is a very interesting question. Basically, I would say to start with that noise is chaotic, whereas musical sound is much more ordered.
Okay.
Now, what is that
you
order?
You mean to say there is no rhythm in noise?
No, rhythm.
In noise?
No, noise is defined scientifically as totally chaotic.
Okay.
So in every sense of the word, it's chaotic. But musical sound is something different. And what makes a particular kind of sound musical? Somehow or other, that depends on our constitution, the way our ears and our face and our brain, all that is constituted.
That's true.
It has been found, and it was found long ago, by, say, Pythagoras, that the ratio 2:3 is very important. That is, there are certain sounds which are consonant to the ear. That is because the human ear and the brain is made in a certain way.
Is accustomed to such kind of...
Yeah, it's made in such a way that certain ratios of frequencies are consonant or harmonious to us. And though the basic ratio is 2:3. And that was found by Aristotle. So what happens is, if you play a particular note, sa, say middle C, sa, then it has a certain number of vibrations per second. So 256 vibrations per second. That's a particular, we call it pitch. If that increases, then we have higher, not shrill, but higher notes like sa, re, ga, ma, pa, dha, ni, sa. They are of higher frequency. So these frequency ratios are very important. Not all ratios are musical.
That's true.
Now, fundamentally, let me tell you how the sa, re, ga, ma, pa, dha, ni, sa, da, or C, if you start with C, C, D, E, F, G, A, B, C. How was this constructed? It was constructed on the ratio 2:3, which is what we call the pancham. So sa to pa, that ratio is very consonant to the human ear. Now, so you start with, say, C. Then the fifth note is G, which is Pancham. Now, what do I mean by fifth note? So the first and second note is a full note. There is a half note between that, which we call C sharp. Then between D and E, there's another half note, which is the E flat or D sharp. But between E and F, it's only a half interval. And then between F and G, again, there's a full interval. There's an F sharp coming in between. So, and then G, A, B, C, right? So anything that has this 1, 1, half 1 interval is a Pancham. Right? So supposing you start with C and you get G. Now you start with G and play the fifth, it will get D. So you start with D and play the fifth, you will get A. And like that, you can go on. It's called the circle of fifths. And you will find all 12 notes, including the sharps and flats, will be produced as each time you play the next fifth. It's fantastic. And the whole of the Western harmony is based on this circle of fifths. But if you go the other way around, instead of going clockwise fifth every time, if you go the other way around, then you will find, for example, C will be followed by F, that will be followed by B flat. These are differences of 4. Because now you're counting from C backwards. So the first 2 notes should be a full note. The second and third should be a full note. The third and fourth should be half. And then comes the fifth. If you count like that, you will see you'll get C, then F, then B flat, and so on. And you can complete the circle that way also. So this ratio of 5 and 4, these are extremely important. That makes a sound musical.
Dr. Ghosh, I want to put this question to you. We are talking about noise and music. What will you call, say, the sound, I won't say noise, the sound of a running train. It's rhythmic and there is a pattern to it. Some people call it noise of a train, but it's also rhythmic. So don't you think there is music in that as well?
Well, I think there can be differences of opinion here, but basically what you are talking about is a periodicity in time. Whereas I was talking about ratios of frequencies. For example, at the same time, I can play C, E, G, the first note, the third note, and the fifth note. That forms what is called a major chord. It sounds extremely nice. So you can build up chords like that also, but all of them are being played at the same time.
Whereas in this,
so this is called polyphony.
It's a periodic.
Whereas our music is linear harmony. It's only purely in time. Our ragas, raginis, or whatever. Western music has another structure over it, where at the same time several notes are being played, and those notes have to be consonant with each other. And there are rules for forming what constitutes a proper chord and what does not. That means everything finally goes by whether it sounds good to the ear or not. And that, as I said, depends on the constitution of the human brain and the entire physiology.
Right. Dr. Ghosh, it's time for a quick break. We'll continue our discussion after the break. Well, time for a quick break now.
India Science is an internet-based science TV channel initiated by the Department of Science and Technology, Government of India, implemented and managed by Vigyan Prasar. India Science on the URL www.indiascience.in is a bilingual channel with content in Hindi and English. It can be accessed on any internet-enabled device. This video platform is dedicated to science and technology knowledge dissemination with a strong commitment to spreading scientific awareness, especially with Indian perspectives, ethos and cultural context. The India Science mobile app can be downloaded from the Google Play Store and Apple Store.
Welcome back to our program Physics of Music. I'm in conversation with Dr. Partha Ghosh. Dr. Ghosh, as far as music and physics is concerned, let's try and understand this aspect of music from the science perspective. I want to talk about waves. How do you visualize music in the form of waves?
Well, as I said right at the beginning, when something emits sound, when something is struck and it's excited, it vibrates and it sets the air into vibration. Now, all vibrations are basically waves, like waves on the surface of water, but they vibrate up and down like this, whereas the wave goes forward. So these are called transverse waves. But sound waves are not like that. Sound waves are what we call longitudinal. That is, they oscillate like this as they propagate.
They move.
Okay. So now, whether it is transverse or longitudinal, all these waves have what is called a wavelength. That is, the difference between the crest of a wave, that is where what we call the amplitude, that is
the height of
the wave, that is the highest. And where does it become highest again? This distance is called a wavelength. And there is also something called the frequency. By the way, the higher the wave amplitude, the more the amplitude, the more the intensity. So if you shout, then the vibrations have a large amplitude. If you talk softly, they will be of smaller amplitude. But what about the frequency? That is how many times it is going up and down in a second. That's called the frequency. And that determines what we call the pitch, whether it's a sa or a re or a ga or a ma or a pa, etc. So the frequency will then go up. So does that answer your question?
Oh yes, indeed. Dr. Ghosh, we've all heard about standing waves.
Yes.
What exactly is a standing wave?
Okay, if you take a string and if you hold the ends fast, you can, like in any string instrument, always the end points are fixed. Then if you excite it, then it will form waves, which will also propagate, but will be reflected at the ends. So
and it will come back?
So this back and forth motion with the amplitudes at the ends will of course be zero, because you're not allowing them to move at all. So that creates what is called a standing wave. And then more oscillations there are between the two fixed points, the higher the frequency of that sound. So the basic one will be simply one wavelength. That's the basic note. Then you can have more and more notes. So that will bring up the pitch.
Dr. Ghosh, you're so well versed with Indian and Western music, but as far as the scales are concerned, they are quite different for these two systems, the musical scales.
Well, yes and no. As I said, the Pythagorean scale is a very natural scale. And in our music, mostly we follow something like a Pythagorean scale, where the first and the fifth note interval is that 2/3 ideal ratio, and so on and so forth. And today, of course, everybody uses the keyboard. So in that sense, everybody is using the same scale. So I don't know what you exactly mean by different scales, but let me tell you that in the normal usual scale which you find in a keyboard, there are 12 notes, the 7 white notes and the 5 black notes. So 12 notes. Those are generated, as I said, by the Pythagorean rule. But in Indian music, you have 22 notes. So like sa, and the next note is Komal Rishabh, right? Now there are 3 Komal Rishabhs which the human ear can actually discern, and the Indians had worked that out. These are called shrutis. Similarly with the other notes.
Yeah.
For example, if you are singing a very early morning raga, then most probably the rishav will be a ati komal rishav because the sun is just rising. Whereas if you sing a purvi or a marva or a shri, something like that, then you are actually, it's an evening. So the sun is going down from higher pitch to lower pitch. So there the komal rishav will be sharper.
Okay.
So these fine things Indians had worked out. For example,
and they have a raga for
they have a raga.
that time
Now,
of the day.
Then I have to explain what a raga is. First of all, there is something called the thart. This is the standard way of doing it. A thart is a certain series of notes in ascending order and a possibly different series of notes on the descending order, or the same. And they have so many, something like 8, 10 tharts. Like a Bhairavi is a thart.
Okay.
Now, Western music also has tharts. They call them modes. And the Bhairavi in Western music is a Phrygian scale.
Okay. So they have equivalent things
There's
in
some.
Western
They're
music
not
as well.
always the same, but there are a lot of equivalences there.
And Dr. Ghosh, you are so well versed.
By the way, let me just say, in Western music, the ascending and descending is always the same, but not in Indian music.
Okay. So that's a
So
major
that
difference.
creates the peculiar mood of a raga. You may go ascending, you can use shuddhani, but while coming down, you skip the shuddhani and go to the komalni.
So it would make
That
it
creates a certain mood, and these kinds of subtleties make up the mood of a raga.
That's true. Dr. Ghosh, you are so well versed with music and more specifically Indian music. I'm sure you would be singing as well as playing some instruments.
Yes, I've been singing since I was a child. I learned my music from mainly my mother.
Okay.
But later on, I got trained by experts in the field. But I also learned how to play a particular instrument. In my young days, a lot of Bollywood music was there, and piano accordion was a great sound. And I got fascinated. So I wanted to learn the piano accordion, and then I was very fortunate that I found a great guru, Mr. V. Balsara.
Okay.
So he taught me the accordion and the basics of Western harmony, the chords, and everything like that.
How easy is it for a scientist and a researcher to, take time out from the busy schedule of research and science, hardcore science at that, and to have time for music?
Well, music is something so dear to us. After all, we are all human beings and we all have emotions. And the emotions are extremely important for us. There's nothing better than music to evoke subtle emotions. So people need those emotions.
And
For a person like,
unknowingly, people hum a tune or a song
hum a
as they
tune.
walk.
Yeah, as they walk.
Yeah, what
Because
happens?
music has a tremendous influence on the human mind, the brain. This has been established scientifically. For example, they have done what are called these fMRIs, functional magnetic resonance imaging of the brain, while
Listening to music.
while listening to music.
Wow.
And they found that of all possible sense signals which you can send, music excites the maximum areas of the brain.
Okay. Wonderful.
So that's why music is very important in training one's mind. And it's sad that these days there's not much scope for teaching music in schools. It's a compulsory thing, which used to be done in Shantiniketan by Tagore. He made it compulsory. I don't know whether he knew about I'm sure he didn't know about fMRI and so on. But being an intuitive genius, he knew that music has a lot of influence on the mind.
That's true.
It's a pity that that kind of wisdom is getting lost.
Dr. Ghosh, it's time for another very quick break. But when we come back from the break, we'll talk about the modern research which is being carried out in the field of science and music. Well, time now for a quick break.
India Science is an internet-based science TV channel initiated by the Department of Science and Technology, Government of India, implemented and managed by Vigyan Prasar. India Science on the URL www.indiascience.in is a bilingual channel with content in Hindi and English. It can be accessed on any internet-enabled device. This video platform is dedicated to science and technology knowledge dissemination with a strong commitment to spreading scientific awareness, especially with Indian perspectives, ethos and cultural context. The India Science mobile app can be downloaded from the Google Play Store and Apple Store.
Welcome back, viewers. You're watching Physics of Music, and I'm in conversation with Dr. Partha Ghosh. Dr. Ghosh, as far as research is concerned, we have, often read about, research being carried out as far as music is concerned from the science perspective and what all can be done, what all is still unexplored. Tell us what is the latest, what's happening at the research front?
As you said, a lot of research is being done on the science or physics of music, starting from the construction of musical instruments. And they are developing. They are becoming better and better every day. In the West, they do a lot. In India, it has started. On the other hand, there are other aspects of music which are also being analyzed. Like, for example, let me give you an example from Indian music. There is an ITC Sangeet Research Academy in Kolkata. They had a unit which was doing scientific work. And one of the remarkable things they did is precisely to check the Shruti system.
Okay.
So the Shruti system is given, the ratios are given, but how do you check that they are the ones which actually the Pandits and Ustads use? So what they did is, they took a particular raga which uses a particular Shruti, let's say Bhairavi, Kamalre or whatever, and they got as many records as possible of the great singers, and they did what is called a pitch extraction.
Okay.
So they could extract the pitches being actually produced by the voice.
Okay.
And so they had a huge database. And then they found that most of the well-known successful singers were more or less using that same frequency.
Okay,
Yeah,
wonderful.
more or less. And they could find that more or less the theoretical Shrutis are actually being followed more or less.
Okay.
Except they found it a bit difficult to extract the pitch from the Komal Dhaivat, which is sung in Darbari Kannada, because that is Andolita.
Okay.
So there's not one note, there's several notes there. So to extract a note from there is very difficult.
Yeah.
So that's one kind of research. Right now, I can only talk about what I know. There's so much more happening in the rest of the world. There is Sir C.V. Raman Center of Physics and Music in Jadavpur University.
Okay.
They are also doing a lot of interesting work, but their work mostly is confined to the neurological aspects. So that is, they do EEG studies while you are listening to music. Again, let me give you one simple example. They studied two ragas, one which is joyful and the other which is sad.
Okay.
Okay.
And the impact on the brain?
And then they made a lot of people hear those clips. and they studied how the brain waves were changing.
Okay.
And they found that when people hear music, the brain waves change and become more complex.
Okay.
So they say the fractal dimension is increasing. So that's an indication that the process of hearing music is associated with complex dynamics of the brain.
That's true.
Then they stopped the music and kept on seeing what was happening to the waves. Of course, those excitations were dying down.
Fade out.
Fade out, right? But they found something extremely interesting.
Okay.
They found out that the excitations of the happy raga went down faster than that of the
sad
raga.
Okay.
So interesting.
So sad ones lingered on, that means. For a moment.
Yeah, sadness lingers more than happiness. We have also done another experiment. In brief, it's like this, that our emotions are ambivalent. Like we do not know whether we are sad or happy or anxious and so on.
Yeah.
So I have a mathematical model of that, which they started testing in Jadavpur. And they found something very interesting, that happy music is invariably, in a very large number of people, happiness is always associated with a little bit of anxiety. Now, this we did not expect.
Okay.
So this is the kind of thing you can find out by doing
things
research.
Coming out, yeah. Dr. Ghosh, on that optimistic note, it's time to wind up this program. Thank you so much for joining us on the show. It's been a real pleasure.
Oh, it was a great pleasure.
Thank you so much. So viewers, that's it. Until we meet next, goodbye.